Started just because it's getting late and we have more material to cover. I'm just going to start and people will come in if they're interested. Taking risks. Okay, so what I want to cover right now is a bit of linear models. And I think this is interesting because it gives you a flavor of what you can do in terms of different regularization for the same kind of forward model. So we're only going to be working with a forward linear model. And I'm going to start a bit with regression. So I'm going to breeze through this and the next session just to leave some room for stuff that Olivier will be talking about that is very interesting. Not that what I'm talking about is not interesting. Okay, so here we're going to look at plotting learning curves, just like Jake did a bit earlier with some linear models. And so I'm going to look at, so that's a fairly simple problem with 50 features, and I'm just generating a simple linear model here and some noise. And I'm applying a linear regression to it and looking at a learning curve. And what you can see here is basically that the score, so here we're looking at scores, so higher is better. The score, if I have less features, if I have less samples in my training set than features, it's simply not working with a linear regression. And I need to have several times more to be able to have a decent prediction score. Okay, so we know this, we need to regularize. So we can regularize using a ridge regression, and we can look at the difference. And we can see that basically ridge regression does much better than a non-regularized linear regression at a very low number of samples. Now, what's important to keep in mind is that here I am not setting the parameter of ridge regression. So I can use a ridge regression CV that Jake already mentioned to automatically set the regularization parameter. And so the intuition is that if I have more data, I need less regularization. If I have less data, I need more regularization. So you can see the performance here. We're getting another significant performance increase. All right, so take-home message, ridge for linear regression, if you don't have any hypotheses, is good. You need to set the amount of regularization. Now, if you're in the specific case that only a few of the features are important for prediction, and I can generate this by putting a bunch of coefficients of my linear model to 0. Right, so I have, out of my 50 ground truth coefficients of my linear model, I have only the 10 first that are non-zero. Then there is another estimator, which is called the Lasso estimator, which is specifically designed to select a small number of features. And you can see that it outperforms significantly the ridge CV for a small number of data points. Now, once again, I did not set the amount of regularization here. So now if I use a Lasso CV object, I can plot once again the learning curve. Now, this is going to take a little while. The ridge CV is super efficient because in the specific case of ridge, you can use a trick to do the cross-validation very, very fast. The Lasso CV is significantly slower. And I've decreased the number of alphas. Alpha is the regularization parameter. I've decreased the number of alphas that is being used to a smaller value just so that it takes less time. All right, so this is going to run. And now, so we're going to have Lasso that gives very sparse models and works well if your ground truth is sparse. Suppose you've observed way too many variables. You don't know exactly what to observe. You observed way too many variables, but you really think that most of them are junk. Lasso is going to be great. Ridge comes with less assumptions, so it's going to fail less often, but won't work as well. Yeah, there is a theorem and a saying in machine learning is that there's no free lunch. Basically, unless you come in with assumptions and those assumptions somewhat match your data, you're not going to be able to perform well. So there is something that sits in between, which is the elastic net. And so the elastic net, there we go. We get our results. I'm going to run this for elastic net and comment here. Okay, so what you can see is that by tuning the Lasso parameter well, you can, in this specific situation where the ground truth is sparse, you're cleanly outperforming the ridge estimator. All right. Take-home message, ground truth sparse, lasso. And if my ground truth is somewhat sparse, I probably want to sit in between ElasticNet and lasso. In between lasso, I mean, and ridge. And this is known as the ElasticNet. And it has a parameter, which is the L1 ratio, that if you set to 1 gives you a lasso, so fully sparse. And if you set to 0, gives you a ridge. So you're going to choose your trade-off between lasso and ridge with ElasticNet. And here I used 0.8. So as a side remark, don't use L1 ratio equals 0. So don't use the ElasticNet estimator to solve a ridge. It's going to work. It's just going to be very inefficient. All right. So let's see what our results look like. Well, it doesn't look like I've got a strong improvement. But in different situations, I would have. If I'd have a less sparse model, I probably would have. All right. So a few comments. One problem, the lasso problem, may have different solvers. Depending on the situation, it may be more interesting to use one solver or the other. We've already seen this with SVM, with the SVC versus linear SVC. With lasso, you've got the lasso and the lasso lars. And really, depending on your situation, one may perform better than the other. Normalization with lasso and to a lesser extent with ridge, it's important to scale your variables. And one nice feature of linear models is that they have a normalize option that does this. What it does is it scales your variable, computes the linear model, and then rescale your coefficients so that they apply to unscaled data. Okay? And we're not going to do, in the interest of time, we're not going to do the exercise. I'm just breezing through this to give you the intuitions with the idea that maybe you're going to remember a bit of this and you can come back later. So one last thing I want to cover with linear models is what I've shown above was for classification, for regression. What if you have a classification problem? Well, let's look at the kind of data we would be working with. Here I've generated data that's 0 or 1. So basically it's my class vector. I can be 0 or 1, and that has noise. And I can fit a line to this data, which is what I've done here. Quite clearly, I'm not fitting the right model to my data. I'm trying to have a straight line go through this. It works, but it's going to be suboptimal. So what we can do is that we can fit a sigmoid through this. Right? So the sigmoid function is basically a smooth version of the Heaviside function. This is known as the logistic regression. And so we have a logistic regression object in here. And I can fit it. It's the red line here. And as a side note, I've used the predict proba to plot the red line here because there's a probabilistic model that tells me that this sigmoid is actually some probabilistic model that I'm trying to fit to my data. All right? So classification with linear models can be done with logistic regression. It can also be done with SVMs, which is a linear model. And one thing that I did not mention, well, that I do mention here, is that the logistic regression has a regularization. Here it's called a penalization. Basically, think of penalization as a specific case of regularization. And it's controlled by the C parameter, just like in SVMs. Very large C means little regularization. And you can set the type of penalty to L2, in which case which is the default, in which case you're doing something that is similar to ridge for classification, or you can set it to L1, in which case you're doing something that's similar to lasso for classification. So you're learning sparse linear models for classification. All right?
In R, you can values for each coefficient. Can you do that easily here?
I don't think in R you can see the p-values for penalized logistic regression. You can see them for non-penalized, right? Because I don't think we know how to compute penalized p-values p-values for non-penalized. So yes, you can see the coefficients. No, you cannot see the p-values because, as far as I know, there are no results on this in the literature.
What about the unpenalized?
We don't have an unpenalized estimator. The bias of Scikit-Learn is that we work only. It's really designed for high-dimensional settings. It's a machine learning toolbox. It's not a statistical toolbox. So we don't have these tools. I think stat models probably has this. So if you're looking for p-values, you probably want stat models and not Scikit-Learn, or you want to bootstrap. So if you got low-dimensional data where standard unpenalized, unbiased statistics are well posed, Scikit-Learn is not the right tool. If you have high-dimensional data where you need penalization, you need bias, Scikit-Learn may be the right tool, but then there is no results out there in terms of p-values. But what I do is I do things like bootstrapping my model, well, permuting my models, which works well. All right, and we're going to skip this exercise. Any extra question on regressions, on linear models, I mean? Can you do deconvolution, as in deblurring an image, for instance? Yeah, okay, so deconvolution is an example of linear model. Basically, I'm observing my data that is convoluted by some blurring kernel or some convolution kernel. This is a linear operation. I want to invert this thing. So this is estimated in a linear model. And so then you want to, indeed, you want to choose out of your linear models. You probably want a regression model. And then you probably, well, depending on your situation, you might want to reg an SciPy or LaSue. Yeah, it doesn't seem like I'm answering the question, but I actually am. It's just formal. I do these things, and it's the exact same tools. The question is, okay, how are you going to wire them up? But yeah, you can if you know how to wire them up. Oops. Okay, now quickly, very quickly, I want to go through unsupervised learning. I'm not going to cover clustering in the interest of time. We've already mentioned it this morning. I'm going to recap a bit things that we've done this morning in terms of dimension reduction. So we've seen PCA this morning. I'm not going to re-mention it. We've seen that it's got things like explained variance ratio. The important point is that it can transform the data to project it to reduce space. What I want to mention, okay, that's going to be fast. What I want to mention is other approaches. Very important in my eyes is the randomized PCA, which we have already mentioned this morning. It's useful because on fairly large data, it's significantly faster than the PCA, very much. It's not exact, but in my experience, it really doesn't matter, and the error is really small compared to the noise in your data. Now, it might be relevant to use other kind of data dimension reduction, like sparse PCA. ICA is not really a dimension reduction algorithm. It's an algorithm to do blind source separation, so it might be useful to change your feature space. And we've seen a bit manifold learning. All right, and I will not cover the exercises. Are there any questions on this, even though I just sped through it?
Just at some chance I saw that the sum of the explained variance ratio sum is not 1. Does that mean anything?
Well, it probably means that when we computed the PCA, we didn't compute all the components. Okay? So if I've computed only the 21st components and my data set has 400 samples and 400 features, I'm probably not explaining all the variance. I think that's it. All right, and now I'm going to switch to something I'm going to cover slightly more slowly, which is pipelining.
These other dimensional reduction techniques that you had in there, your documentation, talk a little bit about those.
Right, yeah. Something that we did not mention is that the documentation tends to be fairly complete. It's basically we refuse to put in code if it doesn't come with a lot of documentation. So yeah, it should cover it.
It has like papers or whatever.
Yeah, it should have papers. It should be hopefully referencing the proper Wikipedia page. It should have examples. It should have tips on practical use. Yeah, let's have a look at it. So Scikit-Learn.org. What do you want? Manifold learning?
Yeah,
Manifold learning is beautiful. I want manifold learning. Jake did it. It's fantastic. So, and it's got the Baloo song. All right. Oops. Yeah. So no. Yeah, so this is a good example of our documentation. So apart from the joke up there, you've got an example that tries to compare different methods, and it's applying manifold learning to the S-curve. And it's comparing a bunch of different methods. So basically here you're taking the S-curve and you're trying to find a manifold embedding of the S-curve. So clearly, I mean, this data is a 2D data set, even though it's embedded in 3D. So can we find a mapping that maps the coordinates in 3D to a 2D mapping? So this is what manifold learning is doing, and you can see a comparison of different algorithms. So don't run home and say, well, LLE never works, MDS never works. Clearly from this example, I can see this. Of course, depending on the setting, one might work better than the other. So as any example in the Scikit-Learn documentation, if you click on it, it will link to the code that generates this example. So all the figures are generated, and you can see below the code that generates it. It may be a bit complicated because, I mean, this is a fairly complete figure, but it's there. You can reproduce it. You can modify it. That's the case for every single example in the Scikit-Learn documentation. Then we have an introduction where we try to explain things. We try to do hand waving, not too much math. Another example on a real-life data set with digits where we're embedding the digits in 2D. And then we're going, each time we're linking to examples. And then we're going to go over the different methods and try each time to give a bit of intuition and a bit of example. And if you're lucky, we discuss the complexity and practical tips. And yeah, and the reference is there. If you're not lucky, you don't have all this. And if you don't have all this, we welcome pull requests. No, seriously, the documentation is extremely important, and we're more than happy. What we don't really want is to add too much math in it. I mean, we think the papers and the books are good enough. What we want are intuitions, practical tips, and things like complexity is often useful. So that's one example. Now, after reading all this, you probably don't know what you want to use on your data. I wouldn't know either. It's a research question or an engineering question. Does that answer your question? This is not the worst part of the documentation. Jake did a fantastic job here.
He didn't say it was the best.
Was that?
He didn't say it was the best.
I don't know what the best is. I don't know. It's probably amongst the best, honestly. But the decomposition one is pretty good too. I think it's Vlad who did this, a Google Summer of Code student. All right. I want to talk a bit about pipelining estimators. It's already been mentioned, but I want to go over it again. So we've seen this morning feature extraction, for instance, feature extraction from text. We've seen running a supervised learner on this. One thing that we haven't covered yet is feature selection. So we've got all these steps. I mean, we could do a PCA for dimensional reduction. We've got all these steps, and it can be really useful to combine them in one big learner. For instance, if you want to do cross-validation to set parameters or to quantify the quality. One thing that you definitely don't want to do is dimension reduction on all your data. And then once you've got reduced data, try to set the parameters of your model. Because when you're doing this, you have a hidden overfit, which is in the dimension reduction. Okay? So each time you have a new train set, you want to do dimension reduction and a supervised estimator. All right, so the feature extraction, I think we've covered it this morning. We can use the TF-IDF vectorizer, which takes text and transforms it to a NumPy array. So it takes a little while, but it's running. Now, one really easy thing to do when you've got, so the problem with this is that you're going to have a huge number of features, basically all the words that you've seen in your corpus. That's probably too much to be useful. So one thing that you can do is to say, well, I'm going to apply a very simple function to each of these feature and y to see if the feature relates somewhat by itself to the target. This could be, for instance, an f-test, any simple test to see if the feature relates to the target. And then you're going to throw away anything that really, really doesn't seem to relate to the target. This is known as univariate feature selection. And the way it works is that you give it a function that will that will score each feature, and you give it the data. And typical functions are f-regression for regression problems, so it's an f-test for regression problem, f-classif for classification problems. And if you have sparse non-negative data, typically what you get with text data, it's really useful to use the chi-square function, chi2. So here we have text data, so we're going to use the chi-square function, and we're going to import the feature selection module from Scikit-Learn.featureSelection and use the select percentile function, giving it the score function, well, the select percentile object estimator, giving it feature selection.chi-square. And we're going to keep only the 5% most useful features. So we're dividing our number of features by 20. Makes everything easier. Maybe not the prediction. Maybe there is some information in those 95% features that we've thrown away. But at least everything runs much faster and with much less memory. So then we can just apply fit transform to our data, and we get a reduced data set. This is really nice. And then we're going to apply this to a supervised learner. OK, so now the idea is that we might want to apply feature extraction, feature selection, and the supervised learner all in one step. And we're going to do this using a pipeline. So we've got in Scikit-Learn.pipeline, we've got the pipeline object. And the way it works is that you give it a list of tuples that are made of a name and an estimator. And the last estimator is going to be used to do the prediction, and all the others are going to be used to do the transform. So here, if I take this data, if I take this pipeline, I'm creating a pipeline with first the vectorizer that I'm going to call vectorize, the feature selector that I'm going to call select, and an SVC for prediction that I'm going to call SVC. And if I apply this to data, it will first vectorize the data, then select, then apply the SVC. This is an object that exposes fit, predict, score, which means that I can stick it in cross-val score or Great Search CV or anything. It's just another learner. So now this is going to take a while because I'm going to do cross-validation and vectorization in the cross-validation. And vectorization takes a little while. So this is going to take a while. So I'll just leave it running, and I'll go on. Now, yeah, so you've seen here that I've put verbosity up to 3 which means that as the thing runs, I get a progress report of how it's running. And if I was not running an IPython notebook, I'd get these things as we go. It's just that the IPython notebook puts the standard error at the end, at least on my version. All right, so this is nice and good, but what I really would like to do is to be able to set the parameters of my pipeline. The reason why I've put all this together in a pipeline is that I may want to choose the percentile of the features that I keep, and I may want to choose some parameter like the gamma. Well, no, this is the linear SVC. Okay, like the C on the SVC, and these may interact. So I may want to choose them together. And so I need to be able to use grid search CV on this, but grid search CV needs names of parameters. So I need to be able to address the parameters I'm trying to set on my pipeline with a name. And the way we do it is that we've given names to our estimators, and we know the names of the parameters. So if I want to set the parameter C of the SVC, in the pipeline, it is known as SVC __ C. So name of the estimator, 2 underscores, name of the parameter. And that's fairly general in Scikit-Learn, where when we're composing estimators, we try to have this convention that there is the name of the estimator and double underscore the name of the parameter if we ever have to set this parameter. Now we can use this as a black box and run the grid search CV. As a side note, this is going to take a while. So we're going to want to try to avoid recomputing several times the same thing. And when I'm changing the C parameter, clearly I don't have to change, I don't have to recompute the transform. It's independent of the C parameter. So one cheap trick that we can use, I use it all the time, is to use memorization of the function that does the work in the selector. So the score function will be given the data and has to reply a score, to return a score. I don't want to recompute this, so I'm using joblib.memory, which will store the results of the score function to the disk, and when given the same data, just recall the results. And I'm putting in selector.score function, I'm putting a memorized version of this one, okay? So this is something that I use a lot when I do parameter selection. Yeah, I've not been executing these things, so I'm going to have problems. All right, and then we're going to run this, and it's going to take a while. I realized when I was writing this example that there's no way we can memorize the different text extractors. So we need to work on that. Because clearly I'm not, the thing that takes more time here is the text extractor, and this is what I should be memorizing. So this is somewhat of a stupid example because I am modifying the last parameter on the last object of the pipeline and only this one. So clearly I should have done the pipeline the other way and put my feeder extraction, my feeder selection, then my grid search, and then my SVM, right? Because I'm really commuting things for no good reason right now, but I just wanted to give the example. All right, so it's running. I think it's going to take a while. You can see that it's printing things because I've asked for standard output. And I think I'm going to stop here and leave it to Olivier.
Okay. All right. So the last part of this session will focus on how to make
stuff faster in general and how to address bigger data set. So the first point we will see is how to speed up the model selection and assessment of models by leveraging distributed computational resources, for instance on the cloud, by using a tool that you might know or not, which is called IPython parallel, which makes it possible to run stuff on a cluster rather than on a single machine. Here, I will first run the examples locally on my laptop by running a cluster locally on my laptop. So to do this, you can follow and do the same. Oops. Yeah, okay. And go to the notebook interface in the cluster tab. And by default, it should be in the 0. It should be stopped. And you can set the number of CPUs, the number of engines that you want to run on your laptop, and start the cluster like this. So a good choice is to pick up the number of CPUs or -1 if you want to still have some some computational resource to be able to read Twitter when it's computing. So back to my example. From? I don't remember the user interface in Canopy. If it's IPython, the default. Oh, you mean the cloud-hosted Canopy? Or, I don't know. If you have a shell, you can also use IP cluster dash engines equals 4, for instance, I think. Start, yeah. I won't do it because I already started a cluster, otherwise, well, maybe it doesn't matter. Let me make this bigger. So IP cluster start dash engines equals 4. No, it's not this. N, okay. N equals 4. Okay. And what it does is that it will create a first process, which is the controller of the cluster. And for each engine, it will fork a new Python process to work. And all the Python processes are connected using 0MQ, which makes it possible to have network separation between the processes. Okay, I'll stop this guy to not. Okay. I don't want to. Okay. So now I should have a cluster running. I just check here that it's still the case. Yes. Okay. So the motivation for this is that when you do grid search, for instance, if you do a linear a kernel SVM training with 2 parameters, for instance, C and gamma, you will need to find for each combination of the 2 parameters, you will need to evaluate the model 3 times if you do 3-fold cross-validation. So, for instance, if C equals 1 and gamma equals 1000 like this, you will run one model that we will train on this fold of the data set and test it on this fold, and do the same for another combination of the folds of the data set, and so on. And you do this for each combination. So here we have just 2 parameters and 3 values. So that's already 9 possibilities. But if you have many parameters, like for text vectorization or trees or whatever, you can have many parameters and the combination will explode. Furthermore, the data set is always the same, but you have 3 copies of the data set. So you might want to read this data set in memory and stick it there for once to avoid reading it from the disk every time, because it's costly. And furthermore, if you have several processes working on the same machine, you want all the same processes to use the same data set as input, not to copy the data set several times in memory, because it might not fit. So those are the 2 problematics that we will try to address during this session. How to distribute this on a cluster of machines, and how to put the data in memory, the read-only data in memory, and not and share it across the processes. So to do this, we will use mostly IPython parallel for the distribution and joblib and NumPy for memory sharing. So the first part is IPython parallel. Okay. The font is a bit big. Okay. So IPython parallel is a package that is a sub-package of IPython. It's used by the notebook and so on to split the front end and the back end. But it makes it possible to have several backends and then do a parallel computation. So in this package, you have a client class that you can instantiate. Okay, so my cluster is not started. This is because I started a new cluster manually and then stopped it, I guess. Okay. Once you have this client, you can measure the length of the client. It's the number of engines in the cluster. By default, if you don't pass any argument to the client class, it will find a JSON file in your IPython configuration folder to know how to connect to the cluster. If you pass an explicit configuration file, it will connect to a remote cluster that you've configured in advance, if you want. So once you have the client in your notebook, you have access to the parallel execution magics, so px. So if you do %px, you can have a block that will be executed in parallel. If you just use a single percentage sign, you can just have one statement. So here in this block, we will import the OS module from the standard library, the socket module, and we will print on standard output the PID of the process and the host name of the machine that is running this code. If I do this, I have a small cluster running on localhost here. I have 4 different engines with 4 different process ID, but all running on the same host. I will show you later how to run on a real cluster on EC2, for instance. With px, you can assign a value to a variable on all the engines in parallel and print the value in parallel. So this is very useful to do interactive computing from the notebook, but we will see later that there is also a programmatic API to write libraries that are able to distribute the load. So I can do any kind of in-place modification of the existing variables, and I can also execute some stuff on a specific engine. So for instance, here I'm using --target -1. It means that this is the last engine that I've provisioned in my cluster. You can use a slice expression here. And then if I do --px, I can see that the engine number 3 has a value of a, which is 4, and the others are still 2. Okay, so this was using the px magics, but we can also use the proper API, for the Python API. So when you slice the client object, you will get a direct view on the cluster. A direct view is an object that references all the engines. It looks like a dictionary, a Python dictionary, where the keys are the variables of the namespace that you are remotely controlling this way. So if I say all engines of A equals 1, I will set the value of the variable A on all the namespaces of all the Python processes to 1 in parallel. And I can access it like a Python dict. I can also define a function locally, which will compute a sum, and apply it in parallel to 2 values, so 11 and 31 here, on all the elements of the cluster, and then fetch the result. The result in this case are asynchronous handlers. And to actually collect the result of the computation, I need to call the get method on the result object. So in this case, it's 42. Yes?
So the all engines view.
Yes.
You said here the A values to 1 is exactly the same like the few lines above, where you say px and then A equal 1.
So the question is the all engines view the same as when I use all engines assignment of the variable A equals 1? Is it the same as this guy here? The answer is yes, but this you can only do it from an interactive IPython session. because this is a IPython magic command, whereas this guy here is just regular Python programming, so you can do it in a library. So the first one is good for interactive debugging of what the engines are doing, and the other one is once you have come up with a meaningful way to do it, you wrap it in a library and you make it possible to reuse. Okay, so the results object that we get in IPython by default are non-blocking. So when you submit stuff to compute on the cluster, you get a handler, and then you can pull this handler to know whether the computation is finished, and when it's finished, get the result or wait for the completion. So here we will define another function that imports the socket module and return the hostname of the machine where it's being executed. If I do this, I can then apply it. I was too fast here. So I apply the function on the view, on the direct view, and so I get the result, and here I get the list of all the results. I block until I fetch the result. This is useful to use this trick of the socket getHostName, because afterwards I can call getDict instead of get, and when I call getDict, I have a mapping between the engine index and the result of my evaluation. So in this case, I can know that the engine 0 is running on host.local, which is my machine. My machine is called host, so that might be a bit confusing. But and so if I invert this dictionary, I have a way to find one engine for each host in my cluster. So here I'm running my whole cluster on a single machine, but this is useful as a pattern when you're running in the distributed session. And this way I can compute a selective view that has only one engine per host. And with this view I can execute commands that will be executed only once per machine, per single machine in the cluster. So in particular, if I do this, pip install user Flask using the exclamation mark, I can install libraries dynamically on my cluster like this from interactive settings if I forgot to install it earlier. What you've seen, something that might be original is the fact that I put import statement inside the definition of my function. The reason I do this is that when I will execute it on the remote cluster, I don't know what has been imported already in the namespace of the engine. So by doing this, I'm making sure that I import my library, my packages when needed. Because when I do this apply, it will actually fetch the function definition from my local notebook process. We'll extract the bytecode, which serialize it, the Python bytecode, serialize it over the network to the engines, and then execute it there, and then pickle the results, and gather the result back to the original Python process. So this way, I make sure that I have all the import statements required automatically. There is an alternative way to do this, is to use this with statement to do imports in parallel and to make sure that all the interactive session on all the cluster have the proper import. In practice, I prefer to put it's a matter of taste. I don't know if we have much time or not. It finished at 5 o'clock. So yeah, we'll skip the exercise. I will just show the answers. So if you have the PSUtil module installed on your system, you can introspect attributes of the running processes on your machine. And in particular, you can introspect how much memory your process is using. So for instance, if you import OS and import PSUtil and call process on the PID of your active process, then you have a method accessors to the amount of memory that is being allocated by the process. So if I do this, I can measure the memory in megabyte that is used by each individual process of my cluster. So I define a function memory MB that introspect the memory and return it in megabyte. I can pass this function to the apply method of my direct view on the cluster and call getDict to get a mapping between the engine number and the memory allocation on each process on the cluster. So here you see that my Python processes, I didn't do anything smart yet, so I just used the regular memory used by a Python process, which is around 30 megabytes. I can do the total sum of the memory used by my engines on the cluster like this. Here, I will use a magic statement to allocate a NumPy array of 80 megabytes on each element of the cluster using like this. So it's 80 megabytes because I'm allocating 10 million 64 floats. So that makes 80 megabytes. And then remeasure the memory occupancy usage of the individual parameters, of the individual engines. And you can see that it's 80 plus the 30 whatever. It's approximately this. So this was the direct view on the cluster. Most of the time when you're using a computational cluster, you want to compute one stuff and one time and not the same stuff many times. So to do this, we will use the load balance view that will find a free engine on the cluster, run the stuff, and gather the result instead of running the same thing everywhere. So here I create an LV object, which is a load balance view. And I will create a function on my local IPython process, which compute the square of the input and wait a bit, just to make it slower. And I can do this by passing my new function to my load balance view and passing the parameter to the function as an additional argument to the apply method. When I do this, I get an asynchronous result, and I can query whether it's ready or not. Here I was too slow, but if I do it quickly, it's false. If I re-execute this guy, it's true. So you can poll the completion this way interactively. And you can also wait for the completion and get the result by calling get. You can also use the map method instead of the apply and passing a collection of arguments here, and it will schedule the execution for all the possible arguments on the cluster in the same way. And you can monitor the progress, the number of elements that have been processed this way. So let me do it. Okay, it's very fast, but all right. And then once you want to block to get the result, you can iterate over the result, and it will block until it fetches all of them, and you can do something with the result inside the iteration loop. Okay, so this was a short introduction to IPython parallel, but you can see that with the load balance view, we will be able to schedule the learning, the fitting of the models, and the performance evaluation in parallel, and fetch the result asynchronously this way. The second step to make it more efficient is to avoid wasting too much memory by memory mapping NumPy array. So to make this quite independent from the previous section, I will stop my cluster, restart it. Yeah, I need to wait. Okay. Okay, sorry. In the new version, you don't need to put a number in the master branch. Okay. So I need to wait a bit for the cluster to start, and I can check that it's actually started by doing len. I got my 4 engines, so it's fine. So I can import NumPy in parallel all the engines, and on the last engine, I will create a memmap arrays. So NumPy has this kind of arrays that are regular NumPy array, except that they are backed by a file on the file system that makes it possible to share the memory. So this is an operating system feature to have a backing file that will be mapped to the address space of the file system, and to have several processes addressing directly the same shared memory. The fact that it's written on the hard drive is just an implementation detail. Most of the time you don't really care. It depends on if you want to use it for persistence or not, but here we will just use it for sharing memory between processes. So the memmap NumPy constructor takes the regular arguments. So you can pass it a shape, a D type, but you need to pass it an additional parameter, which is the mode. And in this case, we will use the creation mode to create a new file and to zero it to 0 value. And I will execute this only on one engine of the cluster. So I will create the file and allocate the array in memory using mmw, because it's in a W mode. I can check using the ls command that this file has been created on the file system. And then I can open the same file, but this time in read-write mode by expecting the file to already exist. The R here makes the assumption that the file already exists. So you don't need to specify the shape. And then we will have 4 NumPy array that actually share the same bit of memory in the computer. So we can check this by changing the value on the mmw and printing the value in parallel. So here I'm doing it on a single engine on the cluster. So I change it on the W, and I see that the change has been reflected in the R version because it's the same memory. And if I do it on the other engines of the cluster, we can see that the memory has been changed everywhere. So I can also change the memory from the R arrays because they have been open in R+ mode. R+ means read and write. And so check that the change has been propagated everywhere because it's the same chunk of memory. Memmap arrays are regular NumPy arrays. So they have the same methods as regular NumPy arrays, like sum, min, standard deviation, and so on. So I can compute this kind of algebraic operation or vector operations. And then I can leverage this to check that the cluster did not allocate too much memory. So here I have a utility function that measures the memory of each process, as we did previously, and another utility function that measures the amount of free memory on each of the hosts of the cluster. When I do this, we can see that we don't have much memory allocated because I allocated just tiny arrays, so it's almost as if I didn't allocate anything. So to check that the memory is actually shared, I will allocate bigger arrays. So on the last engine of my cluster, I will allocate 10 million floats, so it's 80 megabytes. So I'll check the almost 80 megabytes. It depends if it's megabits, megabytes and stuff like this. Okay. And check that the memory of the cluster, I think at this point it shouldn't have changed because it's actually just created on the file system and not yet used in memory because we didn't access the actual data. So right now the memory usage it's still the same. If I open it from in a read mode on all the engines, you can see that it's very, very fast because it's just addressing the buffer from the processes, but it doesn't access the data on the hard drive. It's just creating a view, a logical view on the data from the hard drive. When I do this, it will actually fetch some of the data to be able to print it, but not all of it. So it's still very fast. I can check the free memory and it's still the same almost because it just fetched this amount of data to be able to print, but nothing more. So the engines they are almost always not using memory. To actually access the data, I can trigger a read of the complete data set by summing the values of this array here. And you can see that now I have 0 as an answer. And it took quite some time. It took 280 milliseconds. And now, if I check the memory consumption of my array, I can see that of my engines, I can see that the last engine has actually allocated the array in memory. And the global memory usage has increased by 80 almost megabytes. Now I can trigger the sum in parallel of all the engines. And this is very fast because the data is already in memory. So I don't have the 200 milliseconds or 300 milliseconds. It's instantaneous because the data is already rounded up in memory. But I can do it in parallel at the same time. And now I can check the memory usage. And according to the file system, it looks like each process is using the 80 megabytes. But if I check the free, it hasn't increased. So this way of reporting the memory usage doesn't take into account the shared memory. But you can check the total memory usage, the total free memory on the host like this. So it was a bit into detail, but this is very powerful. This is something that few NumPy users know about NumPy, but you can actually share memory between processes, and that makes it very interesting to do a big-ish data processing. There is a better way to deal with memory mapping is to use joblib. Because with NumPy, you have to allocate your NumPy array manually, but sometimes you have a more complex object, like a Python class with attributes that are NumPy array. In the case of Scikit-Learn, each estimator is a Python class, and most of the coefficients are NumPy arrays. And you can create those elements as usual. And by using the pickling functionality of joblib, you can serialize this data structure on a hard drive. And we will actually have the data structure here in the first pickle file, and each NumPy array will be stored in a separate file. And each of those separate files we will be able to memory map them. To memory map using joblib, you can just pass the memmap mode argument when you reload the data structure. So that makes it trivial to memory map any kind of complex set of NumPy arrays. And in particular, this is useful for the SciPy sparse matrices because there are just a bunch of 3 different NumPy arrays, so you can memory map them this way.
Will that not work with masked arrays?
Masked arrays, no. Because masked arrays, they do copy of whenever you access, they do a copy. So you would have to mask to serialize it on the hard drive and memory map the result. So this is life.
Just to clarify, I'm really interested in the SciPy sparse.
Yes?
SciPy sparse. So if I just had my float zeros be a SciPy sparse matrix, it would introspectively find the NumPy
Yeah.
and roll those up.
Yeah, basically if you, I will import SciPy sparse as SP, sp.csr matrix of np random normal size of 1010, for instance. Oops. Sorry. What's wrong here? Okay, I miss it. Yeah. So I will call it, I don't know, sparse A. This guy here, I will just execute it. So it's a SciPy sparse matrix. You can see that internally it has a data attribute, which is the NumPy array with all the non-zero values. And it also has indices array, which is an integer array of the location of the non-zero values. And as it's a 2-dimensional data structure, we also need ENDPTR, PTR, which is a much smaller array to be able to slice the two others to find the location. I won't go into details, but SciPy sparse matrix basically is just 3 NumPy arrays. 2 of them are quite big, and the last one is much smaller usually. So if you have this guy, you can just do joblib.dump of SPA to some file. I will put it in the temp folder, SPA. And joblib by default will return the file names that it used to do the persistence. And so the first one is the pickle file, and for each individual NumPy array from the data structure, it created a new file that you can memory map. Okay. No more question? So we will combine those 2 utilities, joblib memory mapping plus IPython parallel distributed processing, to do the computation of cross-validation. So the first step that we will do is pre-compute the fold of the cross-validation, because here you can see that when we want to do parameter evaluation, for each parameter combination, we will use the 3 different cross-validation folds, 3 possible combinations. So we will pre-compute those 3 guys because they are the same here, the same here, and the same here, to be able to share them between the different engines in the cluster. So to do this, we will just wrap the regular, it's a bit too long. We will just wrap the regular Scikit-Learn cross-validation utility. So in this case, I'm using shuffle split, which is a nice one. You could use k-fold cross-validation also, or whatever. And I will create the CV object, create a list of file names where I will store the result of the materialization of the cross-validation, and use joblib dump to store them on the hard drive, and return the list of the file names from this process. So this is a utility function. It's called persist CV splits. So I will try to use this on the digits dataset as usual. And it will return a set of, here I did 5 iteration of cross-validation. So I want to do 5 iteration of cross-validation. So I will have 5 shuffled split version of my dataset. And actually, internally, it's using different NumPy arrays, because here I have a tuple for the X train, Y train, X test, Y test. So for each fold, I have 4 NumPy arrays. So once I have this on the hard drive, I can memory map it and access the X train as a memory map without loading the data in memory, without copying the data too many times. So once I have this dataset memory mapped, I can do a grid search. So here I will define a grid search with 2 parameters, for 2 parameters at the same time, C and gamma. So I will look for 4 value of C and 5 values of gamma on a log space. And I can use the itergrid utility class from Scikit-Learn to explode all the combinations of those parameters in a list. So itergrid takes a dict of ranges and iterates over all the combinations. And it supports the fact that you have conditional usage. For instance, if you have a kernel, RBF kernel, you want C and gamma, but if you have a linear kernel, you don't want to use gamma. So it's a bit smarter than just iterating. So by using this itergrid, I will be able to wrap it in a function, utility function, that will load the data from the hard drive using the memory mapping. So here I'm using copy and write. You could just use read. So from a specific CV split, a specific model for specific parameters, I will load a CV split from the hard drive, set the model parameters using the setParam function, feed the model, compute the validation score on the test set, on the validation set. Test and validation is the same in this case, and return the score. So this is the individual function that will be executed on each element of the cluster. And the grid search function here is my own implementation of grid search, so that will take a load balanced view on the cluster, the model to grid search, the list of cross-validation folds as file names, and the parameter grids. It will use the iter grid utility to explode the list of combinations and run the task in parallel by using the load balance view apply method and calling the compute evaluation on each for each parameter evaluation. So I will execute those because I forgot. And I will try it on the digits dataset that I've prepared earlier. So when I do this, I get all parameters and all tasks. It's a bit complicated, but basically all tasks is the list of tasks that have been submitted on the cluster. I can monitor the progress by defining a new function that will iterate over the task and check whether it's ready or not by querying this method. And here I can see that it was very fast, so it's already finished. But for larger grid, it would take more time, and you would be able to introspect the progress this way. Once I have all my results in the tasks, I can sort them by mean scores. I can compute the mean validation score by iterating over the results, and sort and find the best model this way. Won't go into too much detail, but here I can find that the best model, the best parameter set, has 99% validation accuracy, and it's for C equals 1 and gamma equals 0.001. So you might not want to do this manually by writing all this code. So it was just to show under the hood how to use IPython parallel to do whatever you want on a very fine-grained level. But I've wrapped this utility in a small library that does exactly what we demonstrated earlier. And furthermore, it uses a trick. It's to randomize the order of the grid so that you can monitor the intermediate progress. And when you see that you cannot get any more improvement of the best result after 1 hour of computation, and you know that you have still 10 hours of computation to do, you can decide to stop. And because we randomized the grid, you have a better chance to find a good model earlier in the process this way. To do this, we will import PyRello, which is just a Python project that you can pip install. If you're using Canopy or Anaconda, I'm not sure if the pip that you have in your path is the right one. So maybe just watch, and later we can discuss if you cannot get it to work. So when I do this, I will just recreate a new client to be independent of the previous stuff. Create a load balance view, the model. Then I have all the utility method functions that I've presented earlier. They have been wrapped in a module called memMapUtils, so that I can prepare my data set on the cluster, warm up the cache. This will warm on each engine in the cluster, make sure that the data is in memory, and then launch the randomized search on the grid. And when I do this, you can introspect the progress by evaluating this. And you can see that it's progressively doing all the 100 evaluation. But you can see that at some point it reaches, it's getting stable on the top because we are getting very good model on the top. So I also added another utility here that displays the best models plus the validation score, the standard deviation of the validation score, the train score, and the standard deviation of the train score, so that you can detect overfitting and underfitting. and also plots for each values of the individual parameters independently of the other, the distribution. So here you can see that gamma is very important for support vector machines, because for some values of gamma, you get 10% accuracy, which is random. So by running this kind of randomized search, you can see earlier that these values of gamma, you can get rid of them, you can prune them off the grid because you're wasting your time evaluating in this region. So that makes it possible to stop the grid, refine the grid search, the parameter search, the parameter space, and focus on the interesting stuff and not waste too many cycles this way. But you have to make sure that you collected enough sample to make sure that they are really bad at this location. And you can see that the value of C here is very much dependent on the value of gamma, and it's less sensitive to the value of C. Yeah, there is no bad value for C. It depends on the value of gamma. So I will also do a benchmark at the end here that will just do exactly the same, but instead of monitoring the progress interactively, I will just wait till the end and display the result. And I will time it to see how much time it takes on my laptop. I think it's around 20 seconds or something. So you can see that it's quite slow. And to make it faster, you can use EC2. And to use a cluster, IPython parallel cluster on EC2, you can use a project which is called a star cluster, which is developed at the MIT. So here we can see 20 seconds. And star cluster makes it very easy to provision a cluster of machines on EC2, on Amazon EC2, to run a distributed grid search if you want. So you can install it using pip. In this example, I will use plugins that have been changed in the development version of Star Cluster, so you actually need the Git version of Star Cluster. You will need credentials for EC2, so you need to put your credit card somewhere. And once you have this, you can use the command line from Star Cluster to create a configuration file. The first time that you run it, it will suggest you to create a configuration file. And then you can generate a SSH key without any password that will be deployed on the cluster to make it possible to connect the machine together. And once you have your SSH key and your configuration file, you can customize the configuration file. So the important parameters are the name of the template, the region where you want to execute this. For EC2, you have many data centers around the world. So you can choose one that is not very used so that the price is cheaper. And then point your SSH key and then give the list of the plugin that you want to deploy in the cluster. And in particular, here we want the IP cluster plugin that makes it possible to run IPython notebook on the cluster plus IPython parallel. I have additional plugin to start and stop the cluster without, to start and stop IPython without starting and stopping the whole cluster because it's much slower. And plus additional plugin to install specific packages like Scikit-Learn, psutil, or Parallel, and whatever. And finally, you have the configuration of the cluster itself. So you pass the SSH key, the name of the Unix user that you want to use, the shell or whatever, the virtual machine image ID, and the size of the nodes. So for instance, I use C1 extra large, which are 8 CPU nodes with 7 gigabyte of memory. And the name of the virtual machine that you can use for this is dependent on the region. So to know which machine to use, you can use Star Cluster list public, and it will give you the list of images that you can provision on each region of EC2. So just pick up one. So for instance, you take the latest Ubuntu 64-bit EBS, and that's fine. Once you have your configuration file up and in your folder, you can start the cluster using this command line. Here it says that I want a cluster with 3 nodes, and I'm bidding on the spot instance market to have a cheaper price. It's a detail, but it matters a lot. So the spot instance market, I won't go into detail, but it makes it possible to provision the machines that are not used by anyone else at a cheaper price by setting the price. And if there is no more free machine at that price, your machine will be turned off and allocated to someone else. So you can play and optimize the cost this way. You can query the history of the price of the machine on each individual region using this command. And then you can do machine learning and linear regression to predict what is your best. OK. So I did that a bit earlier here. And when you run this command, it will allocate. I will make it bigger. It will allocate the machines and launch a spot instance request. So it's a bid on the marketplace for virtual machines. And once you get your virtual machines up and running, it will start installing stuff on it. And in particular, it will install NFS to share all the file system, the home folders, which makes it very easy to share data between the nodes. And it will start the IPython notebook and the IPython edges everywhere. And you will get the HTTP address of the notebook and the password to connect to it. And also a command line here, as a code snippet that makes it possible to run your own IPython client on your local machine connected to the remote server. Here I will just use the notebook on the remote server directly, it's easier. And then it installs the packages that I want, Parallel, PSUtil, and Scikit-Learn. So in total, it took, I don't know, 5 minutes to get my cluster up and running with everything installed and ready. So it's very, very nice. Once I have this, I can go back here to this tab, and you can see here that it's the same notebook. I downloaded it, I git cloned, and so on. And I can rerun the same stuff that we did locally on EC2 instead. So in the configuration file of the cluster, I have a plugin to install pip packages this way. There is another plugin to install Debian packages. For instance, for SciPy, you don't want to compile the Fortran stuff from pip. It takes a long time. So you can use Debian packages instead. You can also SSH into the machine, install whatever you want, and then snapshot the virtual image and reuse it later. It's even faster to provision the next time. We'll make this a bit bigger. Yeah, and I will rerun this part. So I import this, I define my client here. Maybe I need to restart IPython because, yeah, it has lost the connection. So here you can see that the length of client now, instead of 4, is 47. And it's 47 because I have 6 machines, each with 8 engines on them. -1 because I want to leave one free CPU for the controller to make it possible to pass the message around the network. So when I have this, I can run the grid search as I did previously. So I warm up the data and pass it around. And you can see that it's already finished, the stuff that took much longer previously. So when I do this, for instance, I do the final benchmark, it's 3 seconds instead of 20. So you can see that for this, I don't have a linear scaling because it was 20 seconds on 4 CPUs on my local machine, and now it's 3 seconds on 47 CPUs. This is because the tasks that I do are very small on a toy data set. On a real-life data set that is big enough, you have linear scalability for grid search.
How much did that cost?
So it costs 10 cents per host and hour. $10. Yeah.
And when you have 47?
I just have 6 machines here. So it's 60 cents per hour. So if you drink 1 coffee at the machine per hour, it's the same price.
That was spot.
Using spot instances. If you use on-demand instance, it's much. It's about 5 to 10 times more expensive. Yes.
Can you talk through how the job-lib memory map is working on the cluster?
Okay, here I am using a star cluster that provisioned the NFS folder for the home folder. So when on the first, when from the Python notebook process, I will go back here. Here, you see, this piece of code here, I execute it locally on the notebook process. And so I'm calling persist TV split, so it loads the data in memory, it does the cross-validation stuff, and it saves it back in the home folder. You can see that it's in a home IP user, and okay. And now it's made available to all of the nodes. But NFS will not copy the stuff over the network unless people request it. So to trigger this transfer in advance and to put it in memory only once, I use this utility function that will call the read. Basically, I memory map the file and I call sum on them to make sure that I read all the data. And so then it's warmed up in cache. It does it only once per node so that I don't have concurrent reads on the hard drive on the various. So it's pretty fast. It's just 100 megabytes per second, so the speed of a hard drive. So, and once it's in memory, you never need to touch the hard drive ever again during the computation.
Are writes still synced like before?
But when we do grid search, we don't do writes of the. Yeah, okay. So if you want to do concurrent writes on a shared memory, you need locks basically not to do dummy stuff. Either you know how you do your writes and you're clever on how you do them and you don't leave locks. For instance, if you just have one engine that writes in the first slice of the array and one engine that writes in the second slice of the array and some stuff like this. Otherwise, you need some kind of synchronization, but it's tricky then. Yes.
Yeah, and anyhow, you really want to avoid this because from the NFS standpoint, it's going to be really bad. You're going to be writing on a file from different nodes. Yeah. So you'd much rather than chunk your files and have several files.
Yeah. So, yeah, if you want to write on local files rather than on NFS. But NFS is good for broadcasting the data around without having to write this. You could write this using IPython parallel. It's quite easy to ship data this way too. Okay, it's just a detail. Okay, what time is it? Okay, 14 minutes. So the last stuff that I want to introduce today is how to scale text classification in particular. Because we will see that this is an example of typical data mining task that you can do with Scikit-Learn, a machine learning task, that has specific issues to scale. But some of the way we will scale them, you can reapply them to any kind of other machine learning algorithm. So the example that we will take is sentiment analysis from Twitter tweets. So sentiment analysis is just we do binary classification to find positive tweets and negative tweets. So tweets that express some kind of positive sentiment with respect to the subject of the tweet, or negative, or neutral. So it's just polarity, it's just binary. It's not very clever. So the scalability issues that we have typically with text classification come from different points. The first point is the memory usage of the text vectorizer. Because the text vectorizer that we use, the TF-IDF vectorizer, has the vocabulary attribute that stores the mapping between the strings, the word representation, the string representation of the features, to the integer values of the column in the sparse matrix. And this, when you have like a large corpus, you have many different words. And if you take n grams of the words, it will be even larger. Will take a lot of memory. And furthermore, it's stored in a Python dict, and Python dict are very slow to deserialize. So if you save it on a hard drive and want to read it later, it's very slow because you need to rehash all the strings in the dictionary. because it's a hash map, basically. So whenever you want to do a large-scale text classification, never use the TF-IDF vectorizer because of this. Furthermore, it's not parallelizable because the vocabulary attribute is a stateful object. When you want to vectorize and learn the feature mapping, you will need to have some kind of synchronization barrier between the processes to make sure that you don't allocate the same word to two different columns. So it will be blocking during the learning of the mapping. So it's another issue. The first one is memory, the second one is CPU parallelization. And furthermore, it's not possible to do online learning because online learning is when you have a bunch of data, you start to vectorize it and fit a model on it, and you throw away the data and fetch another bunch of data, vectorize and classify, and incrementally learn the model, so that you never have the whole data set in memory because you stream over the data when you do this. Unfortunately, because of the vocabulary, you don't know from the first batch all the different words that you will see in the coming batch. So you don't know how many dimensions you will have, and so the number of dimensions should be dynamical, and unfortunately, most Scikit-Learn classifiers, they want fixed number of dimensions. They cannot use a dynamic number of dimensions. So because of those three problems, we need an alternative to the vectorizer. So TF-IDF vectorizer is the same as conv vectorizer. They are very similar. They are all based on a vocabulary. When you fit something with the conv vectorizer, I need to restart because it was. I'm running on EC2 here. Okay, when you fit a conv vectorizer on a piece of data, here it's a corpus of one single sentence. I have the vocabulary that has the Python dict with the memory mapping between the word and the feature indices. Then I can call transform and I get the usual representation as we did previously. I will skip this a bit. Yeah, okay, I will just skip this. We will see later how to fix this. So to illustrate this problem, we will use a Twitter dataset, which is from a website called Sentiment140. And you have it on a USB key or in the fetch data script. And you can access those files and see what's the size of the files on a hard drive. And you can see that there is a big no emoticon CSV file that is 200 megabytes. And this CSV file is basically a collection of tweets that have been collected by searching for the positive emoticon and the negative emoticon. And then we strip the emoticon, and then we have labeled data set with many tweets. So it's called the emoticon trick. If you want to train a sentiment analysis classifier for social networks, it's the best way to get started. But it's kind of noisy because sometimes in some tweets the emoticon is the only non-neutral word. So there are many stuff that are actually neutral that are labeled positive or negative. So here I have a Python function that will parse this CSV file. It's a bit of a pain because all the positive examples are at the beginning and the negative examples are at the end. So as I don't want to load all of this in memory, I'll need to read the beginning, then stop, and then skip through till I find the negative example and start to read some of them, and then collect the two and shuffle them to have a data set that is small enough to fit in memory and identically distributed. So this is why this function is a bit complex. So when I do this, it takes a bit of time because it's parsing the CSV file. Okay. So I will just check the size of the text train all variable and the size of a target train all variables to check that I have as many text samples as I have labels. So here I have 200,000 tweets, positive and negative mixed. I can display some of them. So That's a bummer. You should have got David Carr some days ago. So anyway, you can see that there is another emoticon that hasn't been stripped here because it's different from the other one. And this one is positive, and the tweet is actually negative. So you can see that this data set is quite noisy, so it will be hard to fit a model on it. But it's better than no data. And I can check that oh, actually, they're all negative, so it might have been a negative emoticon in front of this. Okay. So I will skip through that, but I need to run them anyway. Okay, so now I have my data set. So in order to work around the problems with the memory, the vocabulary-based vectorizer, we will use the hashing trick. The hashing trick is, instead of using a Python dict to map the words to integer indices, we will use a hash function. So it's an implicit infinite dictionary that lives in the logical space. So for instance, the is mapped to the colon 700 whatever, and so on. So all the possible words will be mapped to a unique column in this space. There might be an issue because we might get some collisions, but if we take a modulo here for the hash function that is big enough, the number of collisions will be small enough that it won't impact the quality of our prediction in practice. And furthermore, the text data is very redundant, so a small amount of collisions is not really an issue. So to implement this in Scikit-Learn, instead of using the hash function directly, here I imported the murmur hash function that is wrapped in Scikit-Learn, I will use the hashing vectorizer that will use this hash function internally to do this. So here I know that my data set is encoded using Latin 1 instead of UTF-8. So I explicitly pass this parameter. This is the only parameter that I pass, but as the usual vectorizer, I have many other parameters for computing n-grams and so on. All the features of the regular vectorizer, you have them, except for the TF-IDF normalization. So you have the ability to debug how the vectorization works exactly as for the other kind of vectorizer. And you can vectorize the whole data set using transform directly. Here we don't need to do fit because it's completely stateless. The mapping between the features to the indices of the feature indices is always the same. It's defined, hard-coded by the hash function. So it's useful because now that it's stateless, we don't have a shared state between parallel processes, so we can do stuff in parallel. And furthermore, it's even faster to vectorize stuff like this. So I don't remember if we have the speed, but I think it's 6 megabytes per second on a regular CPU. And so you can see that I have my whole data set, actually my small data set, that have been vectorized this way. So now that I have my vectorizer, I can import a classifier. So in this case, I will use passive-aggressive classifier, which is a very nice linear classifier. It's a bit better than a linear support vector machine because it has fewer sensitivity to the hyperparameter and the learning rate when you're, whatever, I skipped that. It's good. So you wrap this vectorizer and the passive-aggressive classifier into a pipeline, and you can fit the pipeline on the raw text values and evaluate it on the validation set this way. So I don't remember how many, I think it's 200,000 tweets. And you can see that it's just in 6 seconds it was able to learn a model on this quite biggish data set from the raw string values. So it hashes everything and learns the model. And we have 74% accuracy on this data set. So the data is quite noisy, so it's hard to be better than this. We can also, here we use the small validation set, but there is also the official test set from the sentiment analysis corpus that we used. And this test data has been labeled by humans. So it's a gold truth data set where humans did check the polarity of each independent tweet to make sure that they are actually positive and negative and not just trusting the emoticons. And so we can see that it's we are measuring the same kind of performance using this n-labeled data. But it's much too small to be able to learn something on this, because it's very, very small, because it's costly to annotate tweets this way. So it's a couple of hundreds of tweets. To compare, so here in this pipeline, I use the hashing vectorizer. As this data set, I subsampled it to have something that can fit in memory on a single machine. I can also use the vocabulary vectorizer and check that the collisions did not impact too much the quality of the predictions. So I will use the regular TF-IDF vectorizer. I will just disable IDF because it's a feature that is not available for this guy, so I want to have a fair comparison between the two. I just want to evaluate whether the collisions are impacting or not. You can see that the speed is slower. It's 10 seconds slower, but the accuracy is the same. So the collisions of the hash function does not impact the predictive accuracy of this model at all. So it's a really nice trick for scaling stuff. And this kind of hashing trick, you can also use it to simulate random projections to reduce the dimensionality. And you can also use it for computing cross product of features to expand nonlinear features. And you can also use it for trigrams and stuff like this. It's not only useful for text, but it can be useful for DNA, for instance. If you do bioinformatics, you will use like a probabilistic data structure like this to be able to scale to a very large data set. Okay, so now that we have a scalable feature extractor, we can do out-of-core learning. Out-of-core learning is a way to fetch some data from the hard drive, vectorize it a bit, just this chunk, incrementally learn our classifier and throw away the data and then fetch the new data this way. To simulate an infinite stream of data that comes from Twitter, for instance, I've written this function, which is an iterator that will just pick up two tweets, one positive, one negative. No, actually, two positive tweets or two negative tweets, and concatenate them and generate a new sample out of this concatenation. So I have an infinite number of positive tweets or negative tweets this way. So it's a way to simulate the actual Twitter feed that is never ending. And I can do online learning on this by sampling from this tweet source, basically. So this class, I have the next batch method, and I will take just the batch size as an argument. So in this case, I will just get 3 tweets that are combined of 2 positive or 2 negative. And I have the label here that has been extracted as well. So now that I'm able to simulate a very large number of tweets, I can do the actual online learning. So to do the online learning, I will create the vectorizer in advance and the classifier in advance. And I will iterate over the number of batches that I want, because I want to stop at some point. And I will get a batch of data, transform it using the vectorizer, partially fit the classifier. So you can see that here I'm calling partial fit instead of fit. There is 2 differences. The first difference is that I'm passing the number of classes that I expect here in advance. And it will not use the actual number of classes from the first mini batch as the total number of classes, but it will just use a fixed number that I pass in advance, which is the number of dimensions from my hash function. And furthermore, the partial fit will run the algorithm, but stop the optimization early. And when I will call it the next time, it will not zero out what it has learned previously. It will start from the previous point and go on a bit, like this. Whereas if I had called fit, it will just forget about the previous stuff and start over again. So not all of the estimators in Scikit-Learn support partial fit. The ones that support it are SGD classifier, passive-aggressive classifier, perceptron for classification. They are all linear models. There is also many batch k-means for clustering. And that's pretty much it right now. Soon we will have the naive Bayesian classifier that should be just a matter of how to add it. And maybe random forest at some point, it should be possible as well, and a couple of others. So I will run this to have a look at what's happening. So here you can see that the kernel is busy, and that I'm starting to collect intermediate result because I'm printing the progress every 100 batches here. So you can see that the score is, as I go through the infinite stream of tweets, is increasing, but it's kind of stochastic because I'm using stochastic gradient descent and I don't see the whole data set. And at some point, you can see that I'm reaching the 74, 75 accuracy that I've found previously. Here I can go a bit above the previous score because I'm generating new samples using my trick of combining positive samples. I'm making new samples to be a bit better. I think it's done. Okay, so now I can also plot the curve, the accuracy of the curve over time. So this is the number of samples that I have seen incrementally, and you can see that my model is converging to this level, so 75% accuracy. Okay, so just to finish, now that we have a stateless vectorizer, we can also use the IPython parallel to run stuff in parallel. So I can vectorize a partition of the data on one machine, then pass it to a classifier on this machine, and do this out of core or not on each individual machine. And at the end, I can compute an aggregate classifier that is just the mean coefficient of all the other classifier and do prediction with this guy. And this is basically a bit like bagging, but instead of sampling with replacement, I'm just partitioning the data. So it's kind of an ensemble method, but it makes it interesting for speeding up the process because I run stuff in parallel, so it's much faster. So I'm still running on my big cluster here. So here, if I access the direct view, I can scatter. I can push partition IDs on all the engines, and I will split my dataset and collect a sample from my dataset that are not the same on each individual engine. So you can see that I have a partition ID number that is different for each engine on the cluster. And I can run the vectorizer in parallel on the CSV file on the cluster. So this is actually doing the parsing and vectorize all the data set, but different slices of the data set in parallel using a hashing vectorizer that is the same on all the model, on all the engines. Then I will run the perceptron classifier and fit it in parallel on each engine independently. At the end, I will be able to have access to as many linear classifier as I have engine in my cluster. So I can gather the classifier using this direct view operation. So it takes a bit of time because it's serializing all the parameters of the classifier over the network back to the controller. So I have many perceptron models like this, and I can finally compute the average linear model by summing the coef attributes of each individual model and summing the intercept attribute of each individual model to get a final linear model. So I'm just cloning the first one and averaging the coefficient here. And with this model, I can compute the score on my label data set. And I get almost 80% accuracy. And what is interesting to check is that I can also compute the score of the individual perceptron that I've used, that I've trained independently on slices of the data. And you can see that all of them, they are quite poor. They are really bad because they just accessed a tiny subsection of the data set. But the average model is much better than anything else. So both were much faster by doing it this way. And furthermore, the aggregate model is an ensemble model, so it's quite good in accuracy at the same time. Okay, so I think that's it. So as we've seen previously, there are other ways to ensemble models. So we've seen boosted, bagging, and there are also stacking, but we haven't stacking implemented in Scikit-Learn yet. So there are other ways to combine models, and you can expect better ways in the future of Scikit-Learn. And there are a couple of limitations of the hashing vectorizer, but I leave you this to read if you want. And I think we should stop here because the time is over. Okay, thank you very much.